Hello everyone, good job in making it to the end of the course. This is going to be the final section on Calculus 1, and it's going to be about the average of value of a function and the relationship with integrals. So imagine that we have a function and then we want to compute the average of the values that we can obtain for that function in the interval a to v. So normally, if we want to do that, we start by dividing the interval in n equals of intervals that they're going to have certain length delta x. And of course, each of those points is what we're going to take into the average. So we're going to pick x1, x2, x3, x up to xn points, and we're going to open those subintervals in there. And then we want to calculate the average of the numbers f of x1, f of x2, f of x3, up to f of xn. So normally, how do you do an average? Well, you take the sum of the numbers that you want to take the average, and you divide by the number of values that you have. So in this case, because we have n values, then we're going to divide by n. We sum from f of x1 up to f of xn, and we divide by n. Now, where do you think this can be used? Well, for example, imagine that you have a function that is representing the temperature, and you're checking by 24 hours. So pretty much, if you do n equals 24, this will mean that we're measuring the temperature readings every hour, and then we're going to make an average of the temperature on the day. But now let's see what happens and how do we relate this to integrals. So if delta x, which is how we split in the intervals, is set to be b minus a over n, then we can write also n as b minus a over delta x. And why is that going to be relevant? Well, because in that way, I can kind of introduce the average in terms of the integration. Notice that I can either take this term and replace it by b minus a over delta x, or if you want to, we can just simply set up b minus a over b minus a, and now we're going to take up b minus a over n, and that's going to give us a delta x over here, which is precisely what's going to happen next. Notice that the sum of the f values, we can express this as the sum from I equals 1 to n of f of xi, and we just pull the delta x by b minus a over n, and so that's where we get this value here, and we're going to be left with 1 over b over a, b minus a. Now, if we let this value increase, this sum gotta look familiar to you. This is a Riemann sum, and so if we let the value of n increase, then we will be computing the average value of a large number of values that are close to each other. So if we make n go to infinity, we're kind of doing the average value of the area under the curve, or all the values that we can collect on the interval a b. So if we make the limit when x goes to infinity of that sum, then that's going to, of course, produce the integral to ab. And if we add the 1 over b minus a value, then we can say that the average value of f in the integral on the interval ab is going to be the average of f equals 1 over b minus a integral of a to b of f of x. So now we don't have to do any more single values, and if we want to take 50 or 100 values, we don't really have to make the sum, but we're just going to use the integration to find out what the mean value, what the average value of the function is going to be on that interval. One example of this, and the example is really simple. We want to find the average value of the function f of x equals 1 plus x squared on the interval minus 1 to 2. So essentially, we're taking all the possible values that 1 plus x squared is going to take in minus 1 to 2, and we're going to find the average of that. Notice that this is an infinite amount of values, and that's why this is so commendable. So we just use the formula, and the average value of f is going to be 1 over 2 minus minus 1, plugging the minus 1 into values, the integral from minus 1 to 2 of 1 plus x squared dx. Now, of course, if we integrate here, this is going to be x plus x cubed over 3. And that's going to be located between minus 1 and 2. And when we plug all those values, this is going to be 2. Okay? So this tells me, hey, the average value of 1 plus x squared over all these values in minus 1 to 2 is actually 2. Now, you might be thinking, well, but this sounds familiar to when we were talking about the mean value theorem or the intermediate value theorem, where we're able to find a particular value that seems to be a value for the function on the interval. And you won't be wrong. That's one of the final conclusions of this product, that this design of the average. And is the fact that if the function is continuous, just because of continuity, if we have a number C, we're going to have a number C in the interval AB, so that f in that point is going to be exactly the average. So the average value is going to be among the values that we're going to reach in the interval, which kind of makes sense, right? So we get a bunch of values in an interval for f. We can reach those values. And what this is saying is, because the function is continuous, we actually need to we can find a specific point where the function is going to be reaching that value. Okay? And so the average formula is this, but if we think about that being a specific value, then we can think of this as f of c equals 1 over b minus a, the integral. Or in another way of writing this is the integral of a to v of f of x dx is f of c times b minus a. And notice that this is going to be, in reality, a consequence of the mean value theorem for the derivatives and the fundamental calculus of theorem as well. This is saying, hey, the integral, the antiderivative of a function, is going to be in terms of the values of the boundary, which is b and a, and a certain average value that the function can reach. So again, we achieve what we want with these theorems of functions, which is the ability to relate specific functions with the values or their antiderivatives. All right, so yeah, this concludes our content for Calculus 1. Make sure to take a look at the practice exercises so you can see a little bit more of how do we use this type of theorem in practice.